Hello, math humans. We're going to do 3.4 today. We're going to be talking about expected value. We are going to calculate expected value, then we're going to determine if a game is fair. We're going to look at house edge, the gambler's fallacy, and the law of large numbers. So if you are playing a slot machine, so whether you like gambling or not, they do create some interesting math problems. So you've lost 10 times in a row. The question is, do you keep playing the same machine because it's due to win, or do you shift to another machine to see if your luck is going to change? Another example that we're going to talk about today is, should you play a game of chance at a carnival? What are the odds, or that's a bad choice of words, what are your chances of winning that game? And then let's say you're trying to raise money for an event and you're going to sell raffle tickets. How much should you charge for those raffle tickets to see if you can make money for your event? So the first thing that we're going to talk about is expected value. So expected value's formal definition is a variable x that can take on the values of x1, x2, or x3. And then we look at the probability of those events, P1, P2, P3. So the expected value is going to be that first value times its probability, plus the second value times its probability, plus however many there are. Maybe another way of writing it is that it is the value of that first event, it'll understand after we do an example, and then multiplied by the probability of that event, and then the value of event 2 multiplied by the probability of event 2, etc., etc. So this information can get to be a little bit cumbersome, so oftentimes it is easiest to manage in a table. So let's start our first example. Oh, look at that. It's magic. It's already written out. So Valley View Elementary is trying to raise money to buy tablets for their classroom. The PTA is going to sell 2,000 raffle tickets at $3 each. First prize is a flat-screen TV worth $500. Second prize is an Android tablet worth $375. And then third prize is an e-reader that's worth $200. And then they're going to give out 5 $25 gift certificates as well. What are the expected winnings for a person who buys one ticket? So we're going to organize this information in a table. So I'm going to write, here's my event, draw my line, and then my first event is that I can win $500. Okay, so that's going to be our event, and then I'm going to look at the probability of that event. Okay, and so it says that I'm going to sell 2,000 raffle tickets. So the probability of winning that $500, right, which would be the TV, is going to be 1 out of 2,000. And then the next column is going to be the value times, I'll put an X there, the probability. So it's going to be, here's my $500, and I'm going to multiply by the 1 over 2,000. And when I do that math and reduce the fraction, I get 0.25. Okay, so that was our first event. The next event is the Android tablet that is the $375. So I'll write my $375. The probability of that, there's 1 of those for the 2,000 tickets sold. And then if I multiply the $375 by the 1 over 2,000, and I reduce that fraction, I get 0.1875. And then I'm going to go to the next prize. So the next prize was an e-reader, so I could win $200. Technically, you win the e-reader, but it's going to work for our example. There are 1 of those 2,000, so it's going to be my 200 times 1 over 2,000. And when I do that math, I get 0.10. My next row, I need a couple more. My next row is that I'm going to win the $25 gift certificates. There are 5 of those, out of the 2,000. So it's going to be my 25 times the 5 over 2,000, and do that math in my calculator, and I get 0.0625. And then I can win nothing, because winning nothing is always a possibility, right? Which seems like it always happens. So I have 8 possibilities of winning. So that means there are 1,992 ways that I can lose that day. And so I'm going to multiply win nothing, so the value is 0, and I'm going to multiply that by the 192 times 2,000, and yes, we know that's 0, but it kind of illustrates the point that winning nothing is a possibility. So then if I add all of these numbers, I get that the sum is going to equal our expected value, and that's going to be 0.60, and you can't see that, sorry, my bad. So that means that our expected value is going to be 0.60, okay? So my expected winnings, how much could I potentially earn, is going to be the cost of the ticket minus the expected value, and that's going to be a negative $3 because I spent $3 on the ticket. I could potentially win, so that's positive, and so my expected winnings are a negative 2.40. So that means that I expect to lose $2.40 for every ticket that I purchase. But the other side of that, and I'm going to turn this over, so let's put me because that looks a little bit better. I'm going to lose potentially $2.40 for every ticket that I purchase. Remember that they cost $3, okay? But if I lose $2.40, that means that the school is going to gain or earn $2.40 for every ticket sold. So that means if I'm going to make $2.40 and I sold 2,000 tickets, then I'm potentially going to earn $4,800 out of my fundraiser, okay? So that is just another way to think about it. So if we look at it from an individual standpoint, based on the statistics, I'm losing $2.40 for every ticket that I purchase. The school then gains that $2.40 for every ticket sold, so the school can potentially make $4,800 for every ticket that they sell. Okay? So we have another example for us, kind of along this same line. A carnival game consists of drawing 2 balls without replacement. And again, remember that this is always one of those key phrases because that changes the number for our probabilities on the second draw from a bag containing 5 red and 8 white balls. If both balls are red, you win $6. If both balls are white, you lose $1.50. Otherwise, you lose $1. Okay? So is this a fair game? It doesn't sound fair, but let's do the math to see if it is or isn't fair. And then what would you expect would happen if you play the game many times? Okay, so this is a conditional probability. And we're going to do this one without replacement. So remember, that means that on the next draw that I have less to choose from. So the probability that both are red is going to be 5 out of 13, because there's 13, 8 plus 5 is 13. 5 out of 13 on the first one, and then 4 out of 13 on the second. Okay, so this is my first draw, and then this is my second draw. Ooh, my bad. I wrote that number wrong. It's 5 out of 12. Good thing I was checking my math. And it goes down 1 because it's no replacement, and this number goes down because if I've already gotten 1 red, then that means there's less red balls to choose from as well. So then this is 20 out of 156, and I think we will just leave it as that, okay? I could reduce it to get 5 out of 39, so either number we will use later. So then the probability of both being white is going to be there are 8, so 8 out of 13 on my first draw, and then 7 out of 12. Remember, I've already drawn 1 white one, so the number of white ones goes down, and then the total number of balls that I have to choose from goes down. So this is 56 out of 156, or 14 out of 39, okay? So now let's kind of look at the rest of the problem, because it seems pretty simple, but it actually turns out to be a little bit more entertaining. So I want to know what's the probability that I get 1 red and 1 white, okay? Well, that's going to be, I can do that a couple of different ways. I could do it by getting a red, then a white, or, this is going to be a key piece, the probability of white, then red, okay? Remember, or means that we add. So if I write this math out, it's going to be the probability of 5 out of 13, and then the probability that there are 8 out of 12. So this is the probability of getting a red and then a white, and then I'm going to add it to the probability of getting a white and then a red, which is 5 out of 12. Okay, so then if I simplify that, I get 40 over 156, and then 40 over 156. That's 80 over 156, which is going to reduce to 20 out of 39. Okay, so if I want to determine my probabilities, okay, then I have to add all of my probabilities together. So I have to add this probability, my 14 out of 39, and then my conditional probability. So if I add 5 out of 39 and 14 out of 39 and 20 out of 39, I get 39 out of 39, which is 100%, which means that it's 1. Okay? Alrighty, so we know that our probabilities all up to add and equal 1, so then I'm going to continue. But to determine if it's fair, okay, that means that my expected value, let me turn the page to make sure that I do this correctly, my expected value has to be equal to 0. So if a game is fair, the expected value has to be 0. So now I'm going to calculate my expected value. Okay, so if I turn this over, all right, so I'm going to do it in a table just because I think it's a little bit easier. Here was my event, and this was the probability of the event. So if I can win $6, that was my first event, and there are 5 of those possibilities, meaning that both balls were red, and so that was 5 out of 39. And we've already calculated these probabilities, okay? And this was both balls were red. The next one is going to be lose $1.50, which means that it's a negative 150, and that was if both balls are white, right? And so that was going to be the 14 out of 39. And then the last one was we lose $1, which means it's a negative $1, and that was all other possibilities, and that's going to be the 20 out of 39. So my expected value, remember we multiply these numbers together, is going to be 6 times 5 out of 39 plus a negative 150 times 14 out of 39, and then plus the negative $1 times the 20, oops, I wrote that badly, out of 39. If I do all that math, being really careful to enter my negatives when I put all of these numbers in my calculator, I get that my expected value is a negative 0.28. And remember we talked about it has to equal 0 for it to be fair. Therefore, this is not a fair game. And I would venture to guess that most carnival games are not a fair game. So let's talk about what this means. That means that you are going to lose 28 cents every time you play. That also means then that the carnival is going to win 28 cents every time you play. It doesn't seem like much money, but if you think about the number of people that go to a carnival and the number of people that try to win, so the more times you play, the more money the carnival makes. Okay? All right. One of the things that we want to talk about is the carnival is what we would call the house, or a casino is going to be called the house. That's who's going to profit from the game, or from the gamble, or however the situation is set up. So the house is always going to be who profits, okay? So the question is, how can casinos make money, okay? So how can casinos make money? So an interesting example would be, oftentimes casinos will publish what their win rates are. So if a casino advertises that it's going to have a 99% payout, right? So in theory, then this would be on a slot machine. What we think is that means that I'm going to make money 99% of the time. But what that actually means is that the expected value is oh so tiny, and it means it's a negative 0.01, because 1 minus the 99 is going to be 0.01. 1 being 100%, there's their 99%. So that means that I'm going to lose a penny, right? That's how we write a penny every time I play. So I'm going to lose a penny every time I play. But if I lose a penny, that means that the casino earns a penny every time I play, right? And so you have to think about this. So if I play, let's say I'm a gambler, and I play 100 games, then my expected value is 100 times the 0.01, which is $1. Oops, there we go. So for every 100 games that I play, I potentially earn $1, right? But remember that the casino is also making money, and so people play hundreds of games, and there are hundreds, probably more than that, hundreds of people playing, and the casinos are open 365 days a year, and they're open 24 hours a day. So casinos, who are the house, are going to get what's called a house edge. I'll write it this way. Okay, a house edge is how much they make every time you play, and so they make a penny every time you play. But even though they only make a penny, lots and lots and lots and lots of pennies equal lots and lots and lots and lots of dollars. So then there's always a moral dilemma attached to casinos. Okay, and you can have this debate. It is shown by research that people that are poorer, that's a hard word to say, tend to frequent casinos. They would make up the majority of the casino population, right? And the casino is giving you lots of free things if you come and play, and so they're going to spend more money. And so the moral dilemma that comes in, is it ethical to be able to participate in a casino activity? Is it ethical to participate in a lottery that a state has? Because the lotteries always claim to give money to education. And so it's an interesting dilemma to talk about the pros and cons of gambling. All right, the next vocabulary word that we want to talk about is called a gambler's fallacy. Okay, and a gambler's fallacy is a mistaken belief, meaning that this is what people think, but it's actually not true, that a streak, okay, and we hear that word a lot when we talk about gambling, of bad luck means that a person's due for a streak of bad luck. And so we're going to look at it statistically, but a gambler's fallacy is if I've had a whole bunch of bad luck, then it's going to turn around and I'm going to have a streak of good luck. And I wrote that badly, sorry, good luck, okay? All right, so as we talk about this, the next thing that we want to talk about before we actually talk about how this works is the law of large numbers. So the law of large numbers basically means that when I have larger trials, meaning larger numbers of attempts, that means that the observed empirical probability is going to basically equal the calculated theoretical probability. So the more times you do a trial, the larger those numbers get, then the theoretical probability and the empirical probability are actually going to equal. So now let's talk about our gambler's fallacy again, and let's talk about it in terms of a streak. Okay? So we're going to talk about tossing a coin. And remember that when I toss a coin, I have two outcomes, either heads or tails. And I have an equally likely chance that it's going to turn out heads or tails. And so I'm going to toss a coin 7 times. Okay? So if I toss a coin 7 times, I want to know what's the probability that I'm going to get 3, 4, 5, 6, 7 heads. Well, the probability of the first head is a half, and then the second head is a half, because the probabilities don't change with each toss. Those probabilities are the same, so that's 3, 6, 7. And if you do that, it's 1 out of 128. So this would be considered a streak because I have gotten a head on 7 consecutive tosses. And so then I multiply all of those together to get 1 over 28, 128. Well, then what happens if I maybe go heads, heads, tails, heads, heads, tails, heads? Well, it's still the same probability. So it's a half and a half. And even though I'm rolling a tail or flipping a tail, the probability is still a half. because it's an equally weighted coin, so my probabilities are the same, and so I get 1 over 128. So a streak is as equally likely to occur as not a streak. And so that shows that streaks are just something that we like to talk about, but it's not statistically relevant. All right, my dears, that is it for today. Thank you for being patient, and I will see you soon.